Hi, this is Wick. Welcome to my poster. Suppose I ask you to keep track of everyone and every object around you. You're going to get overwhelmed really fast. Our visual system is generally bad at detecting changes in rapidly changing environment. It expects continuity and stability. In a more natural setting, one is more goal-oriented and representations of the environment are generated on the fly. A fundamental question here is, how much working memory capacity is available during naturalistic tasks? We used a memory game to investigate this question, and you might be familiar with this game. It's also known as the concentration game, where observers find pairs by flipping cards. We had a twist, of course. We have the search button, as you can see here, and when observers come across a pair, they must turn the search button on to collect that pair. Otherwise, they miss it. So here this person is still looking for pairs. You can see not every card has a match or a pair. And now they press the search button on. And the match is made. So the data here is the number of clicks you make when the search button is on or when you're in search mode to collect a pair. Now you can imagine if you have perfect memory, it will take you one click to collect a pair in search mode. A little more about the game. Each board had 24 cards, and each board had a unique set of items and a variable number of pairs. On average, there were 6 pairs per board. So observers had to press the next board button to move on to a new trial or a new board. The objective was to find 100 pairs as fast as you can, and there were 2 versions of this game. One is the vigilant version, a demo of which you've just seen. That is, when the observer finds the second item of a pair, they must turn search button on to find the pair, or else the pair disappears. And then there's the automatic version, where observers had no control over the search button. It turned on automatically when observer clicked on the second item of a pair. So here is a quick sequence where a pair is collected, and let's define some terms. So what we're calling the memory set size is the number of items from the start of the board until the second member of a pair is flipped. That's the memory set size, the number of new items you've seen. So here the memory set size is 6. And what we're calling search clicks is the number of card flips required to rediscover the first member of a pair. So here the number of search clicks is 3. Then we plot the memory set size against the average clicks you make in search mode. So you can see that the memory set size as you're collecting or flipping cards in a board is evolving, it's increasing. So here's the data. So as you can see, the average clicks made in search mode in the automatic condition is near the chance level because people are relying on the search button more to collect the pairs. And in the vigilant condition, the average number of clicks requires much lower than the automatic condition. This just means that the observers are using more working memory in the vigilant condition, as expected. So how do we estimate K? We used a simple model where K varies between 1 and 23. And for each K, if a target item is in the model's memory, the model just requires 1 click to retrieve it, otherwise it guesses. And we input the human click data to get the right memory set size distribution. So now there are 3 cases. Either the model requires more number of clicks to collect a pair, or it requires less number of clicks than the human observers to collect the pair, or they require equal number of clicks. And the question is, who finds the pair, model or human? So we don't consider the third case if they're equal. We just look at the win proportions. So this is the data for that. On the x-axis, you have capacity, and the y-axis, you have the win proportion. And if you look at the curves on the screen, there are mirror images of each other. So model plus human equals to 1. And here's the intuition. When the model K is too small, the human observers will win more often. When the model has a small memory, suppose K is equal to 1, the humans will obviously win more because the humans, we don't have a working memory size of 1. And if k is too large, the model, if the model has a k of 23, it will win more than the human. So none of those are the correct estimate of k. At 50% mark, both the model and the humans win equally often. Therefore, to estimate k, that would be the line I would pick to estimate k. So for the vigilant condition, using this strategy, k is around 7 or 8, and in the automatic condition, k is around 3 to 4. So in conclusion, partial knowledge that my target is somewhere over there gives observers an effective memory capacity of greater than 4, which they use if and when they need to. So that's the walkthrough of my poster. Thank you for listening. Bye.